I made a little change to a title because if I keep title same, it's probably a bit boring since I give a talk on the Graph TA workshop on Wednesday. So firstly, let me still introduce a little bit about IBM TJ Watson Research Center because it's like many of us will meet there later this year. This is the headquarters of IBM Research Department where we have over 2,000 researchers in this beautiful building working on different research areas. And this building or this site is pretty close to the New York City, so I have been asked for many times where is exactly the IBM Watson TJ Watson Research Center. Actually, it's about half an hour drive from the New York City, so it's pretty convenient. So regarding the graph efforts in our research, especially in our team, okay, we have been using the various graph data set, including the LDBC data set for research. However, sometimes it's a little more beyond the benchmarking for the graph queries or graph database systems, because IBM is also a vendor of hardware, a vendor of a system, and a vendor of software. So people from different research areas come to me ask, okay, graph is very useful in their research area as well, but they want to see how we can help them. So this is one example I want illustrate today. In this case, we actually use the LDBC dataset, and we provide a set of representative graph analytic implementations. Then this package is given to the architecture people who are designing the next generation of processors. Because the current processor actually is more support for traditional scientific compute. It's not really designed for graph. So they want to take into consideration of the graph computation patterns. So basically, what they do is that based on the System G, which is like a graph database, we are developing for high-performance graph computing, right? We kind of pull out the analytic part, then we use the data set generated from LDBC SMB. And so right now we have a fixed input graph, we have a fixed implementation of the graph analytics. Then the only thing that will affect the result is the platform, more specifically the architecture. So that's why this package is useful for the architecture people and they like it. So we figure out a lot of details. Of course, I don't want to go to the mailing hardware details in this talk, but those features that we figured out using the LDBC dataset do help. It's really helpful. Let me skip the details. Then we actually make this small part of the work open sourced, which is available on the GitHub. Everybody can download it and try it. There have a small benchmark for the multi-core processors and a small benchmark for the GPUs. All under the same underneath let's say graph layer. Okay, the graph layer here is not graph database, just more like a framework. And if you want to play with some graph algorithms, I think there's quite a few nice graph implementations, graph algorithm implementations. Okay. Now let's jump back to what we are really want to talk about today. It's about our current work for temporal graph research. We have been talking about the basic graph operations in IBM System G, which can process property graphs and help users to quickly build some large-scale graph analytic algorithms or implementations. So, but here we want to emphasize its usability in the temporal graph area, because we notice that almost for every single real use cases, the graph is always dynamic, and the dynamics itself bring us a lot of useful information. So for if you talk to some analysts, they are more interested in knowing how the cluster in a social network changes over time, instead of what is the cluster at this given time point. actually. So in this case, we have to, really record historical information of the graph, how it changes and how its structure and changes and its property information could change it. Okay, so in this way, we could, apply some machine learning algorithms for the let's say temporal inference. Given a certain time, the information at a certain time, so can we infer the unobservable or latent information? Okay, so underneath we need a temporal graph support, and then on the top we have interesting, machine learning algorithms or analytics. This is also useful for some data management. For example, for some database, we know they support bytecode feature, and in certain applications, the bytecode queries are really useful. And since we keeps all the historical information in the temporal graph, of course, it's very easy to pull out the graph at a certain time stamp. Then we could answer, at that time stamp or that time period, what is knowledge you know, and you know it from what time, and it ends at what time. So that gives it bytecode feature information. Of course, eventually we have to go back to the let's see, the data structure, how we organize the graph on the disk and in the memory, so that we can really do the query efficiently. So for different graph databases, we can see different data structures, like Neo4j, Spark-C, and Titan. And the different structure, of course, leads to different performance. Like what Titan is doing is probably good for locality in terms of data loading and the saving. But in query, if there's hundreds of properties and you only use 2, there's a big overhead behind. So in our case, of course, we have to store the graph structure itself, like the collections among the vertices. We also have to store the properties. And somehow we kind of store properties in separate ways, the structures, to handle the different, dynamics in terms of graph structure change and property information change. More, we have to handle the connections between timestamps, meaning at each timestamp we have a slice of a graph. So a graph and time t, a vertex and time t may influence a vertex and time t plus 1. So actually there's a link between a vertex and time t plus 1. Right. So in this case, we will have to handle more connections. So we extend the graph representation in the original IBM system G, where we handle the internal connections within a timestamp. So it's like we have additional label where you can think about it. Of course, we process a little bit differently, where we store the edges and its information across different timestamps. So in this way, we can kind of have a connection, or let's say some pointers which points to the different information, like edge list and the properties for different vertices. And we could have multiple caches. Those caches are small actually, just give us a pointer, but by using these caches, it takes almost no time to explore data across different, of the graph at different timestamps. Okay, so it's easier to compare a graph at 2 different timestamps. It's easy to see for a particular vertex how it changes over time. Then that information can be easily represented as using some maybe tables is kind of is a misleading term, but it's something like that. Then the backend, in terms of backend, we can use a different KV store or something to do it. But actually, in our case, we implemented the backend ourselves from scratch, so it does deliver high performance. Then for some so what is feature of this kind of data organization that actually supports some really interesting computation. Like one of the very typical analysis on temporal graph, then we want to, do the, for example, observe the information flow from time 0 to time Tn, right? So typically, the way what we do is that we propagate information from one timestamp to the next time and next following timestamp one by one. So considering if we have observed a lot of timestamps, let's say dozens of thousands or even millions of timestamps, this propagation itself takes a lot of time. So when we have enough computing resources like cores or processors, can we accelerate it? It sounds like a little bit difficult, and at the first thought, because this is a one step ahead computation. One timestamp is dependent on the previous one. Okay, so there's no parallel activities, but actually using some techniques like point jumping, we could do that. We accelerate the computation time to an order of n over log n, where n is the number of timestamps we have. Okay, so originally we need n timestamps to process all data, but right now we only need log n timestamps. So it saves a lot of data. And there's some details regarding, for this diagram is an illustration of how we can perform, for example, a random walk over a temporal graph. And this technique can easily be extended for example, computing the page rank over a temporal graph. Okay, then. Well, maybe I need to give a little bit more information if time is okay, right? Okay, so what we do for it, like a random walk, typically is that we will have a state transition matrix, which gives us for example, given a state, which is like row, then what's the probability we will go to the next state? Okay, and in this case, actually, because it's a temporal graph. So we have a really big matrix where it's kind of like a diagonal matrix. Each pi in the diagonal corresponds to a one timestamp here. Thank you. Okay, so just keep in mind that pi in the diagonal is not just like a single number; it's a submatrix, and that matrix corresponds to a time series here. And then the beta I and the gamma I on the side, upper side and the lower side, gives the probability that we will jump from one timestamp to the next timestamp. Okay, and the p of course gives the probability that we just jump over within a timestamp. So a typical way for computing this static probability is that we have each vertex has a importance factor. Let's say we can represent as a vector. Let's say x. Then if we have x time multiplied with p equal to x, then we reach the stable status. So we can solve it using a linear solver. It's doable, but given this size, which is extremely large for dynamically graph and where the number of nodes and the edges is high, then this solver actually takes a lot of time. So it's better to perform this computation over the time structure, over the graph structure directly. And what we do is that, for example, the first time, every timestamp will transfer their data, give their own data to the next one in the time axis. Then in the second step, each one will give information to its ground child, let's say ground child, then ground child. So in this case, after log n steps, everyone will have all the information from all its processors. Predecessors. Okay, this is how on the bottom. It's how it works, the pointer jumping works, and why it could give us accelerations or speed up, even though the computation itself seems like there's no parallel activities. So it's really interesting and helps in reality. So this is still ongoing work, but we do have some experiments we did using interesting healthcare data set. So we observed a bunch of data from the pensions. And of course, these pensions are kind of related to each other according to their features of diseases. And the time gap, well, the time period we observe is like 24 months. So as time goes by, we use this inference or information propagation over temporal graphs. As we can see, as time goes by, the accuracy increases. So more specifically on these figures, we can see that the error, prediction error, decreases. Well, regarding the two figures, if there's any information not clear, you can think about the x-axis is the time, and the y-axis is the score, which indicates the situation of a patient in terms of its disease. Okay. Then we have a baseline. The baseline score gives us, if we propagate those information without using the temporal information over a graph or without the temporal graph, then its error rate actually is much higher compared to the situation where we do use the temporal graph data. So, well, this experiment is preliminary, but it's interesting, and we will show. Hopefully, next time we will show more information, especially the performance, like how fast it could be on our computers. So this concludes my talk. Thank you.
Thank you very much. So, is there any question for Ying? I do have one question. How that scalability will behave with your solution towards this time-oriented management of the graph?
Yeah, it's a good question regarding the scalability for the temporal graph processing. Actually, in terms of the scalability, it's also related to how we organize the graph data. So in our graph data organization, it supports the horizontal partition of the graph because we organize our data using a vertex-centric manner. So we, for each vertex, we store as the edge list along with it, the property along with it, and also the edges across different times along with it. Yeah. So basically, we could partition the vertices into different groups and allocate this partition to let's say a shard on different processors. Of course, and then of course the different ways of partitioning can impact scalability because it results in different communication amount. Then there's we also use some technologies. For example, if we know some operations is not really computational intensive, it's more like data intensive. So instead of we transfer data from one shard to another shard, from one processor to another processor, we will send the computation itself let's say a serialized class to the remote computer. Then the computer will deserialize it and process the local data. In this case, we just need to send, for example, a serialized class which is pretty small. Then we avoid a lot of communication. Yeah, so that actually helps us for the distributed graph processing and make it scales up. Yeah.
Thank you.
Sure.
Is there any other question, Peter?
So we are also interested in thinking about temporal aspects in graphs for benchmarking purposes. So did you actually use SNB for temporal experiments already?
So currently, it's I'm using the healthcare data set because
Sorry.
it's okay. So currently, I'm using the healthcare data set because the temporal graph feature is still undergoing, and for this case, we know more about the specific requirements for users. But what you said makes, of course, when the code is stable, we want to try large data set, and the SMB is what we are interested in. So just like in the first talk, in first part of my talk, we show how we can enrich the SMB data set for the other teams of our research center. I think one thing for the LDBC data set is that we could control its size. This is some if we simply use some other like a real data set, we don't have such a feature. So this is something I think is kind of like a interesting point.
Thanks. Well, a very short, unrelated question. So you said you pointed to this GraphBig open source release.
Mm-hmm.
I looked at it very, very shortly. So it contains algorithms.
Mm-hmm.
Do they assume that you have System G, or is it standalone kind of implementation?
So the GraphBig is a standalone, so you don't have to use the System G underneath because unless you want to pay, yeah. So it's free. But the interesting part is that the API, programming API in the system in the GraphBig, which is called OpenG, is very, very similar. I can't say it's exactly the same, but it's very, very similar to System G. So anything that you implemented using the GraphBig, it's very easy to port it onto System G to enjoy. Then you will have higher performance and you will have the persistency feature. Yeah.
Thanks.
Sure.
So thank you very much.
Thank you.